Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing olefin polymerization in the last few lectures, and in this regard in the previous lecture we have looked at one big discovery in the field of olefin polymerization, which is Ziegler-Natta catalysis, and in that respect we have seen the sequence of events starting from Aufbau reaction, the nickel effect that led to the initial discovery of Ziegler-Natta catalysis, and subsequently we have also looked into these contributions made by Carl Ziegler with regard to the Ziegler-Natta catalysis, which is mainly centered around polymerization of ethylene. So, in today's lecture we are going to go further and look into the contributions of Natta, Giulio Natta with regard to the Ziegler-Natta catalysis, which is centered around propylene. In this we had observed Ziegler's work is on ethylene to polyethylene, HDPE, molar masses 10 to the power 4 to 10 to the power 5 Dalton, and the catalyst is titanium tetrachloride diethyl aluminum chloride at 25 degrees centigrade and 1 bar pressure, that gives rise to this polyethylene. Now, the main limitation and the active species for this is surface alkylated beta TiCl3 catalyst. Now, this had been the Ziegler's contribution in the Ziegler-Natta catalysis, and he is the first one to have identified this polymerization procedure of ethylene to give polyethylene of very high molecular weight, and that too under ambient condition using titanium tetrachloride and diethyl aluminum chloride at 1 bar pressure, and the active species is supposed to be surface alkylated beta titanium 3 a catalyst, which is generated from the reaction of TiCl4 and diethyl aluminum chloride. One of the major limitation of this Ziegler's method is that they had very broad distribution of molecular weight and their polydispersity index are very high, PDI or polydispersity index is high. So, the polymers were of a broad range of distribution of chain length. Now, and then the emphasis became on developing single site catalyst which will have uniform active species, and as a result one can get narrow distribution of molecular weight, and those are called low PDI polymers. So, this had been the work of Ziegler. Now, the NATA's contribution had been in polyethylene to polypropylene using these the catalyst. So, and usually the low density polypropylene were obtained by radical method. Other than this, other methods like radical polymerization gives low molecular weight oils. And so with respect to this Ziegler-Natta polymerization provided access to this polypropylene of high molecular weight and of different properties in terms of hardness, softness and so on and so forth. The another important thing which is which comes into play is the orientation of this methyl group in the propylene polymer, and which is absent in case of the ethylene polymerization to polyethylene. So, there are different possibilities in which the methyl group can orient with respect to each other. That is one important thing, and based on that the polymer properties of polypropylene varies depending on how this methyl group gets stacked up. So, there are a classification of polypropylene polymer based on the arrangement of the methyl group, and we are going to be looking at these different classification. The next thing which comes into play is that how different classes of polymers are produced using this titanium catalyst. So, how does the catalyst site work to get these different kind of polypropylenes as shown over here. So, now we are going to talk about the various type of polypropylene classes of polypropylene polymers that exist, and this is termed as now these the properties of polypropylene are dependent on density, hardness, ductility as well as the tacticity. So, the various types of polypropylene polymers that can be present depending on the methyl branching is shown below. The first one is the arrangement like this, where all the methyl groups are pointed towards one direction. These are called isotactic polymer, and all the carbon atoms have same configuration. And this is called IPP. The next has arrangements of this type. This is called symbiotic. And this is called this has regular alternation of configuration. So, if one methyl is coming up, the other methyl is going down, and then the other is coming up and the other is going down. So, this kind of arrangement is called symbiotic, whereas in the first one it was isotactic, where all the thing was coming up. So, this is called symbiotic polypiperidine or SPP. The third one has three region where some of them are coming up together and the others are going down. So, these are called stereo block. And alternation of isotactic C4 to C10 blocks, C100 with different configuration. And these are called STPP. The fourth one are so this is called hemiisotactic, stereo centers one, 3, 5, 7 are isotactic and 2, 4, 6, 8 are atactic, and this is called HIPP, hemiisotactic. And the fifth one this is called atactic, irregular statistical, change in configuration, and this is called APP, atactic. Now, all of these so many varieties in terms of ethylene, polyethylene, we had only 3 varieties, LDP, LLDP, HDP, and in terms of polypropylene, apart from the molecular weight, we have another variety based on the stereoregularity of this methyl group. So, we have the first one, which is isotactic, where all the methyl groups are in the same direction, followed by the syndiotactic, when all the methyl groups are in alternate arrangement. Then we have stereo block polypropylene, where there is a blocks of the same same side oriented methyl groups, followed by another block of different side oriented methyl group. Then we have hemiisotactic, in which half of the centers are isotactic, that means they occur in a regular arrangement towards one side, and the other half alternating other half is atactic, that means they can appear in any direction, followed by the last one, which is a completely irregular statistical change in configuration, which is called atactic polypropylene. So, these configuration characterization, this has been what was capitalized by Nata in explaining putting forth the polypropylene polymerization. This stereochemical feature of this polypropylene polymer is what is seen as Nata's contribution in this whole Ziegler-Natta discovery. Hence, because owing to the structure, stereoisomers of polypropylene differ in physical properties and in their applications. For example, their structure relationships are also different. For example, isotactic and syndiotactic polypropylenes are usually crystalline. Are usually crystalline owing to their helical structure. Whereas atactic polypropylene is are amorphous. Now this is a kind of a very interesting thing that how come the important question over here is why the polypropylene produced by Ziegler-Natta process is isotactic. Now, statistically it can form any of the 5 thing. So, the important question which arises at this juncture is why the polypropylene produced by Ziegler-Natta process is isotactic. The answer is lies in the mechanism, and what is important is that free a coordination site cis to titanium carbon bond is crucial. So, that there has to be a cis site which is crucial for achieving crucible to cis size to be present to titanium chlorine bond, and which is crucial to the formation of this. So, there is a free coordination sites cis to titanium is important for producing this isotactic polymer. So, with this let me just sort of take a look at how this polymerization proceeds. Now, this has a CH2 CH3, this is the polymer chain, and to this the propylene comes CH3 and binds, and this is the vacant site, and then it goes through this 4-membered transition state CH2 CH2 CH3 CH3. So, it goes through 4 membered transition state to give the product Cl CH2 CH CH3 CH2 CH2 CH3 P, and now, so first there was a vacant site over here where the ethylene added. Now, there is a vacant site over here where another molecule of ethylene comes and sits, and then again the subsequent insertion of this into the polymer chain happens. So, first is insertion of this into this and then the insertion of this. So, first this is first insertion and then second insertion and then this proceeds further, whereas the termination, this is propagation followed by termination, which happens CH2 CH CH3 polymer. This is alpha beta and this gives elimination beta hydride elimination to give titanium chloride, chloride, chloride and hydride along with CH3 CH2 P, where P is growing polymer chain. And this whole mechanism is called as the Earlman-Cauchy mechanism. So, with this we come to end of discussion of today's class, and what we see is what we have discussed today in the class is that we are focused on Natta's contribution in polyethylene. We have also looked at the different classification of polyethylene that exist based on the orientation of the methyl branches, and also we have looked into the question as to why this Ziegler-Natta process gives isotactic very ordered polyethylene, and the answer to that lies in the fact that there has to be a cis vacant site vacant site cis to the titanium carbon bond, which will have the polymer chain where this propylene will come and insert, and because of the presence of the cis site that the catalyst is able to distinguish between the approach the facial two faces of the propane that approach and selectively make a isotactic polymer. So, more on this stereoregular polymerization of Ziegler-Natta process for for propylene as we meet next. With this I would like to once again thank you for being in the class, and we are going to be looking at this Ziegler-Natta polymerization in bit more detail, with taking some more complex and relevant examples with regard to this the development of this catalyst as we proceed with the discussion in the next class. Till then, goodbye and thank you.